Bosch piezo fuel injectors are the cornerstone of modern diesel direct injection engines. To control the injection valves, the new common rail injectors use rapid action actuators made of piezo crystals, usually quartz, to control the injection valve. The piezo crystals expand with an electrical field. The electronically controlled piezo actuator switches 5 times as fast as a regular gasoline injector valve. Bosch has built the actuator into the body of the injector itself. The movement of the piezo pintle is transmitted non-mechanically, and therefore entirely without friction to the rapidly switching nozzle needle. This doubles the injector's switching speed, allowing a more precise measurement of the amount of fuel injected, and thus leading to a reduction in harmful combustion products. This is the essence of clean diesel injection systems. The forces required to open and close the nozzle needle cannot be generated by the solenoid valve on its own. The nozzle needle is therefore indirectly triggered via a hydraulic force amplification system. In other words, the piezo device triggers a smaller fuel chamber, and the pressure differential in this small chamber then triggers the main fuel injector pintle. With the solenoid valve closed, the small chamber and the rail chamber are at the same pressure. The nozzle needle is forced against its seat by a spring. When the solenoid valve opens, fuel flows from the valve control cavity and into the fuel return. So in a sense, the small chamber loses pressure. In this way, the top of the main injector is at a lower pressure, and the pintle tip. When this happens, the fuel rail pressure overcomes the spring force, and the injector opens. So, the feed pressure prevents complete pressure equalization, and the pressure in the cavity drops. Again, the excess pressure in the main chamber overcomes the spring force, and lifts the needle so that injection can start. When the solenoid valve piezo stack is no longer energized, it closes the opening to the fuel return, or small chamber. The force applied to the top of the injector pintle increases, along with the increasing pressure in the valve control cavity, or small chamber. The needle closes and injection then stops. The way this system works is that the piezo crystal stack actuates a small hydraulic chamber, and the small chamber pressure differential then actuates the main pintle. This is done since the piezo stack does not have the power needed to open the main pintle on its own.
Audi has a leading role in diesel technology based on a competitive edge that goes back decades. Audi engineers have achieved decisive breakthroughs time and time again, the largest being the world's first TDI engine in a car, introduced by Audi in 1989. TDI is today a strong, economic and efficient alternative for the power engine of the future. The modern common rail system sends 1,800 bar of injection pressure to the fuel injector needles with piezo injectors, which distribute the power optimally in the combustion chamber. Due to the extremely quick reaction time in millisecond range, up to 5 separate injection processes can be achieved per cycle, which are also variable. In addition to the main injection processes, pre- and post-injection processes are also possible. Pre-injection moderates the acoustic hardness, the so-called rattling of the combustion process. Post-injection is specifically to raise the temperature of the exhaust gas and therefore for regeneration of the standard diesel particulate filter. These factors together allow exact, highly efficient combustion. The TDI turbochargers are part of a new generation. In the intake manifold of the engine, there are swirl flaps which are used to regulate the inflow of air in order to achieve optimal combustion. This use of technology allows high maximum torque of 5,400 RPM and clearly improves the thermodynamics in the combustion chambers. It allows the engine to run with a very high rate of back-fed and heavily cooled exhaust gas. The colder combustion with lower oxygen content massively lowers the output of nitrous oxide. Economy, low emissions, large power output, realized by forward-looking technologies. The latest generation TDI engines are highly efficient, high-tech power units.
Diesel combustion chambers come in two main types, direct and indirect injection. Both are designed to promote turbulence, to help the compressed air and injected fuel mix well. Engines using direct injection have cylinder heads with a flat face. The combustion chamber is formed in the top of the piston. Sometimes the rim of the piston provides squish, forcing the air to the centre of the combustion chamber. This causes turbulence as fuel is injected into the cylinder. In indirect injection, the piston is fairly flat or has a shallow cavity. The main combustion chamber is between the cylinder head and the top of the piston, but a smaller separate chamber is in the head. Fuel is injected into this smaller chamber. It can have various designs. This is a swirl chamber. It's spherical and connected to the main chamber by an angled passage. Both the injector and glow plug are screwed into the head. The glow plug preheats the air inside to help start the engine. During compression, the spherical shape makes the air swirl in the chamber. This helps make a better mixture of the air and fuel, which improves combustion. This combustion chamber is divided into a main combustion chamber and an air cell joined by a throat. The injector is in the throat. When injection commences, combustion pressure forces the air to flow from the air cell, where it mixes with fuel from the injector. The rush of air from the air cell produces a rotary motion of gas in the main chamber, which helps make combustion more efficient. This pre-combustion chamber is screwed into the cylinder head. The injector is mounted in the upper end. Injection occurs near the top of the compression stroke. Only part of the fuel is burned in the pre-combustion chamber because of the limited amount of air there. The high rise in pressure forces burning fuel into the main chamber. This happens very rapidly, which helps make more efficient combustion.
Selama operasi yang sebenarnya, enjin selalu bekerja dengan beban. Governor memastikan apakah RPM enjin sudah benar untuk beban tersebut dengan menggerakkan rack ke posisi fuel on atau fuel off agar RPM-nya tepat. Mekanisme timing advance memantau peningkatan atau penurunan RPM lalu merubah timing penyemprotan bahan bakar untuk memulai burn window pada saat yang tepat.